So this is about using our Jupyter spreadsheets a bit more, but as I do, I'm going to try to use it so that you can understand what's going on with the sample mean more. So that you will learn how to do some things with respect to pandas and Jupyter notebooks, but this will, I hope, open your eyes a bit as to what the sample mean is all about. Okay, so we start out, we're going to import pandas as PD, and we're going to import numpy as, or numpy as np, because we're going to do some higher powered math with it. But we're also going to put percentage sign matplotlib inline. This will help us with the placement of our graphics. You may have noticed sometimes I really have to whack my keyboard to get the graphs to print out. This makes that easier. I'm going to start out and now set a population size. I'm going to construct some population data. I'm going to set it to be equal to 1 million. And Python allows you to use underscore as you do put out your number to help you group the digits and make your numbers more readable. So 1 underscore 000 underscore 000. So that's a population size of 1 million. I'm going to be working with sample sizes of 30. And I'm going to now, on this last line, I'm going to have a population of data, and it's going to be random data. So np.random allows me to generate some random numbers. With uniform, these numbers are going to be evenly spread between 50 and 100, and I'm going to have population size of them, and so that's going to be 1 million numbers I'm going to have. So I shift, I enter, and it thinks a minute, and I have 1 million random numbers stored. Okay, now let's see. I'm going to take this population and I'm going to set up put it temporarily in a data frame. I'm not setting this data frame equal to anything. You see PD data frame, and in it I have this dictionary, which is just a dictionary with a single entry, and that's going to be keyed through population. And this population data here, this list of numbers, is what I'm putting in it. Okay, and so this is my data frame. Off that data frame, I'm only going to want to look at the one column in it, and I'm going to plot a histogram that has 5 bins. Okay, and I shift and I enter, and hey, here is my graph of that. And yeah, each of the height of each of these bars represents the number of data items, and each one of my 5 bins has like 200,000 data items. If I double the number of bins, okay, meaning I'll have twice as many places as I put in 10. Okay, I shift and enter, and again they only come up to 100,000 in my height here, but they're still just about the same number in all of those. So this is why was this uniform? Because the data is evenly distributed on the interval from 0 to 5. I have just as many items between 50 and 60 as I do between 80 and 90, for example. Okay. Now, I'm going to take a random sample of these. So np.random.choice, and I'm choosing from my population, and I am choosing 30 of them, a random choice, just like if you went out into a country with 1 million people in it and chose 30 at random to ask them something. Shift, enter, and so here are is my random choice here. This is what a sample looks like. Now, so it's taking a random sample for me. Now, I don't want just one random sample. I want to be taking 1,000 samples. So let me show you here. This is kind of complicated, but it's going to give us a dictionary of samples with 1,000 things in it. Okay, so let's just take a look here. I go dict. Notice it's in green here. This is because it's a keyword, and it'll be a dict function, and then inside that I have two things. First, I got this. Let's see, these parentheses where on the first half with a comma between the two entries. Before that comma, I have sample string, and I have these curly braces here. I put a dot there, and then a format of I. So what this the dot format means that this I will be substituted in here, whatever value that I takes on. Okay, after the comma in parentheses, I have my random choice. So with each of these sample things, I'm going to associate a sample, right, of my sample size. It'll be 30. And then after I have closed off these parentheses, I'll start for I in range 1000. The range 1000 means I'll start with 0 and I'll go up to 999, substituting each of these values in for I here. So this is kind of complicated, and so I will practice more before I make you do this on your own. So shift, enter, and so I have my 1,000 samples of size 30 are in my samples. I'm now going to take this dictionary and start a sample data frame with it. So pd.dataframe, we've used that before. And let's put samples inside the parentheses. I shift, I enter, and so the data frame. Let's see what it looks like. Okay, shift, enter. I look at the head of it. And so I start off sample 0, sample 1, then it goes sample 10. What happens is it puts the headings in alphabetical order instead of numerical order along with the numbers. So it does have there is a sample 2 in here somewhere. It just got left out because of the way that headings are put in alphabetical order. Okay. Now, what I want to do is, let's see, take the mean of this. So when I put sample df, mean parentheses, this is going to take the mean of every column. Okay. And see every single column, right? Its average has been taken, and there it is. We have 1,000 of them. I don't want to list out all 1,000 now, so I'll put dot HEAD parentheses shift, and sure we have a shorter version of it now. Now I'm going to create another data frame. Okay, data frame mean, and here I'm just starting it as an empty data frame, but on the next one I'm gonna say I'm gonna put one column in it, and that column is going to be equal to contain all of the values that I get by taking the means of this other. So I just now set this and I shift, and there I go. and I want to see how the values in this are distributed. So I do it as I did before, Shift, Enter. Okay. And so we see here, these are how the numbers are distributed. Okay. And notice, whereas before they were uniform, now they are clumped around the middle. And so it looks like they're clumped around this average value. Yeah, and they should. A uniform distribution where their numbers are uniformly distributed between 0 and 100, its mean is 75. Well, look, this thing is just, the bulk of its value is over 75, and the farther away from 75 you get, the more sparse the numbers are. Let's do this with more bins. Let's put 12 bins in it to make, it turns out to make a prettier graph. And so here you see it does thin out. This is called a bell-shaped curve because it's shaped like a bell, the lips of the bell being very thin and the top of the bell being thicker. Okay. Now, I want to show you something else. This is kind of what standard deviation is good for. Okay, so I start out, I'm going to have the mean mu, the np.mean of the population. So this is the mean of my population data. Then I'm going to have the standard error. The standard error is the standard deviation of the population divided by the square root of the sample size. And so here I'm using the sample standard deviation of the population as an estimate, but for this size of a population, it's a very good estimate. Okay, then I'm going to define a function called the z-score. We'll talk more about the z-score later, but the z-score, you take the element, you take the mean of the population, and then you divide it by the standard error. Okay. And then we do the sample mean, give it a new column that's called z-score. And so what we do now to each of the means we have, we're going to apply this z-score function. And then what does the resulting graph look like? Okay, well, it looks like this. And so my z-scores are much, much smaller. My z-scores are going to be, almost all of them will be between 3 and -3. Okay, and again, when I explain the z-score and what it does, you'll understand what's going on a bit better. But what I want to do, I want to count how these z-scores are distributed. And I could do it just by taking a histogram of this. In fact, I may in fact do that before we're done, add that column. Right now, I'm going to add a new column called floor. What the floor does, it will take each of these take each number put in it and round it down to the largest integer that's still smaller than this function. Okay, and so we'll do that and see. Okay, so I've rounded these down, and now I'm going to group by the floor function and count them, count how many of these that hit each level, and then look and see how that's distributed. And you see when the z-score is 0 or -1 or -1 or 1.43, these numbers are small. Most of our data is between here and here. Okay, just know we only have 26, 37, 39 of our 1,000 data items are outside, farther away than these 2 standard deviations from the mean. Okay, so this is what standard deviations are good for. They give us a absolute measure of how far our data is from the mean. Now, let me take a quick look here. If I do sample mean parenthesis z-score dot hist, dot plot dot hist have to check my hist, and let me put 12 bins, bins equal 12, shift enter, and again this is what it looks like. Okay, we're clumped around the middle. Most of our data clusters around the mean, around where the z-score is equal to 0. You'll be learning a lot more about z-score later.